Let's talk a little bit about working with integer numbers in C#. Up until now, you've been seeing me use the int data type throughout all the examples that we've encountered up until now, but there are plenty of other ways of working with integer numbers. And the only real difference between the various data types for working with integers is the size of the variable container, which basically dictates the range of numbers that that variable can hold. For example, there's bytes, which are 8 bits in size, and they are unsigned by default. They are 0 to 255. That's just 8 bits, and 255 is the largest number that you can hold inside of a byte. Along with a byte is the S byte, which means signed byte. That's also 8 bits, and it can hold a number from negative 128 to 127. So byte and S byte are both the same size. It's just a question of which one you want to use when you know that the number is only going to be positive or if the number might be signed. Similarly, there's a data type called a short. The short is 16 bits, or 2 bytes, and that can hold negative 32,768 up to 32,767. Now notice, unlike byte, shorts are signed by default. So if you want to use an unsigned version of this, you have to use the ushort, which stands for unsigned short. It's also 16 bits, and it can hold a number from 0 to 65,535. The next step up from there is, of course, the int, which is what you've been seeing me use all this time. It's 32 bits, and it can hold from negative 2.1 billion to 2.1 billion. And there is, of course, an unsigned version of it, which is uint for unsigned integer. It's also 32 bits. And since it's unsigned, it can hold from 0 up to about 4.3 billion. That's a pretty good range of data, but suppose we want to handle numbers that are larger than 4.3 billion. Well, no, we are not out of luck. There are other data types that we can use. There's, of course, the long, which is 64 bits, and it has a range of, well, really, 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 really big. You can see those numbers right there. It goes from that negative 9 up to the positive 9, whatever that number even is. I have no idea what the name of that number is, but it's really, really huge. In addition to the long, there's the unsigned version of this, which is the ulong. It's also 64 bits, and it can handle from 0 to, well, even really, really bigger. But of course, there's also floating point numbers, not just integers. Usually we use floating point numbers for things like decimals and other kinds of fractional numbers. And to do that, there's a float number type. And when you declare a float number, you have to put a little lowercase f on the end. And you can see here I'm declaring a floating point number of 123.45. And it has 7 digits of precision from the range that I've shown there. There's also a double, which is another type of floating point number, but it has 15 to 16 digits of precision. And you can see that when you declare it, you have to put the little d on the end to distinguish it from the float. Floats have f's, doubles have d. So in this case, I've got a double number, which has much higher precision than the floating point. And then finally, there's the decimal number. The decimal number is an interesting beast because it actually works in base 10 and not base 2 like the other kinds of floating point number types that C# works with. And to declare a decimal number, you simply say decimal and then the name of the variable. And here I've got 123.45, and you put the little lowercase m on the end, which indicates that it is a decimal number. Decimal numbers have 28 to 29 digits of precision, making them very, very high accurate numbers. In addition to these data types, there are some special floating point values that you should be aware of. The first of these is NaN, which means not a number. If a floating point variable gets into a state where you've either tried to divide by 0 or some other kind of error happens, then the variable is set to NaN, which means not a number. There's also a positive infinity and a negative infinity setting. For example, if you have a variable f defined to be of type float, you can do things like say, hey, if f is less than float.positive infinity. You can also check to see if float is equal to not a number. You can do things like float is positive infinity or is negative infinity. And these are useful for things like sorting algorithms. You can also check to see if the float is not a number. Again, because these floating point data types, along with all the other primitive data types, derive from system.object, they have all these great methods and properties built into the language. Okay, let's talk a little bit about why you'd use floating points such as floats or doubles versus something like decimal, because one of the things you'll find is that with floating point numbers, and I'm not going to go too deep into this because it's a bit of an advanced subject, but because of the way computers work, computers calculate values using base 2 notation rather than base 10 like we humans do. And that can lead to a loss of precision for certain kinds of transactions. So let's take a look at a piece of code that explains how that happens. So I've got my double versus decimal project open here. And here's the program file, and I've got my snippets open as well. So what I'm going to do is copy these lines of code over to my main function. So what we're going to do in this example is compare how double precision works with decimal precision. And like I said earlier, internally, computers represent numbers having to do with base 2 notation. This is the famed zeros and ones you've probably heard about if you've ever worked with software before. But what it essentially means is that because of the way numbers are calculated on a microprocessor, you can sometimes lose precision when working with certain data types. And I'm going to show you a difference of how decimals are handled versus how doubles are handled. So right here at the top of my function, I've got two variables, 20th and 1. And you can see that I've defined 20th and 1 to be types double. And so I've got 0.2f and 1.0f. And what I'm going to do is write out what 1 minus 20th is. So 1.0 minus 0.2, you would expect that to be equal to 0.8, right? So let's see how the double data type and decimal data type compare when doing the same kind of option. Because down here, I've got two variables, decimals, which are 1/20th and the real one. So now I've got the same kind of calculation. I've got 1.0 subtracting off 0.2 each time. The only thing that's different is in one case they're doubles, in one case they are decimals. So let's save this and let's run it. And you can see that in the first case, the 1.0 minus 0.2 when using a double results in 0.799999999, whatever, a whole bunch of high precision numbers here. But obviously there's a loss of precision when using a double number. Whereas in the case of the decimal, the 1.0 minus 0.2 did in fact result in 0.8 as you'd expect. And again, that's because the decimal data type works with base 10 numbers naturally, whereas doubles work with base 2 numbers. Now you might be saying to yourself, oh my God, is this some kind of a bug in .NET? Is this a huge shortcoming of C#? It's not. You'll find this in lots of different computer languages that work with floating point numbers, whether it's C or Objective-C or Java, it doesn't really matter. This is just one of the ways that computers keep track of numbers internally. So let's go back and take a look at a chart of when you'd want to use double versus when you'd want to use decimal. Let's take a look at why double and decimal are different from each other. First, in the nature of precision, doubles are 15 to 16 figures of precision, where decimals are 28 to 29 figures. So you've got double the amount of precision in a decimal number as you do a double. In internal format, in other words, how the microprocessor on the computer works with the number, in doubles, it's base 2. In decimals, it's base 10. So far, it's looking like you might never want to use a double, right? I mean, after all, you've got higher precision, it's using base 10. Speed, however, is an important factor to consider. Because doubles are native to the CPU, in other words, they're native in the fact that they use base 2 notation, the speed when using doubles is very, very, very fast. Decimals, on the other hand, because they work in base 10 and have to be converted to and from the native processor format, can be up to 10 times slower than using doubles. So what are they good for? Well, scientific calculations can usually be executed quite accurately and quite fast using doubles. So they're good for scientific calculations, whereas decimal numbers are good for financial calculations. When you're dealing with hundreds of millions or billions of dollars, or even small amounts, but many, many, many times, these differences in precision and accuracy on the CPU can add up to real money. So because decimals work in base 10 and are very highly accurate when working with floating point numbers, they are ideal for being used in financial calculations. You can use doubles and other floating point numbers for scientific calculations.